We are now going to cover an important paper that's considered a milestone in our field. This paper has a provocative title. An image is worth 16 by 16 words. Transformers for image recognition at scale. So I'll first give you the main intuition. The intuition is this. We have so far seen the transformers being used for words, for language, natural language processing. For natural language processing, the transformers caused quite a revolution, isn't it? It was a sea change. If you guys remember how language translation or speech recognition or any of these things used to be in the 2016s, and you compare it to now, there has been a sea change. Would you guys agree? Like today, you can see ChatGPT, etc. These are all transformer models. So the question that is asked is, from a practical perspective, can the transformer architecture be used or harnessed to the service of computer vision also? Now, it begs the question, why in the world would we do that? Don't we have a wonderful architecture, the CNN that we just talked about? It works really well. So why would we do that? And obviously, you can say the answer to that is, you have to at least try and do a comparison. That's another way. Or a more theoretical answer is this. Let's see, if transformers understand language, language can be expressed in words. They can also be expressed visually. Literally, a picture is worth 1,000 words, as the saying goes, isn't it? So in other words, a picture is also a visual language. It's basically a visual language. It's a language too. Okay? So therefore, in principle, we should somehow be able to figure out how to extend transformers to the visual language. And in fact, the visual language understanding today is very much transformer based. It has CNNs as well as transformers. These are the two key architectures that you will see dominate this field, with transformers becoming more and more influential in this space. Okay? And in this course, we'll go through many interesting architectures. You'll see that what we are going to learn today is the basics. But when you hybridize it with many other things like autoencoders, vector quantization, etc., by the time we are done with multimodal learning, you will be doing things like diffusion models for images, image generation, and for video generation. So that's a long journey we are going to take in the next, it will take a month to do that journey. Right. So let us start with this paper, and that's where the title is, an image is worth 16 by 16 words. Instead of saying 1,000 words, it says 16 by 16. So that gives us a clue of where it is going. I'll start with the abstract. As usual, I won't cover the whole paper line by line, but we'll get to the core ideas. While the transformer architecture has become the de facto standard for natural language processing tasks, its application to computer vision remains limited. In vision, attention is either applied in conjunction with convolutional network or used to replace certain components of convolutional networks while keeping their overall structure in place. I'll pause here with a little reflection. Do you remember the paper, the original transformer paper was called Attention is All You Need? What was the history of it? See, attention was discovered 3-4 years prior to that paper. It was discovered in 2014. What people were doing with RNNs, with LSTMs, is they found that if you hybridize, if you throw in attention into the mix, then those LSTMs, RNNs did better than what, better at their tasks. So generally, the orthodoxy was, of course, if you're doing language, if you're doing natural language processing, the go-to architecture is RNNs, LSTMs, etc. Right? And different rewirings of them. It was the orthodoxy. No one questioned that you could build something purely out of attention. When attention came as a useful functionality, they shoehorned it on top of it, right? And so that led to better results. The real value of the attention is all you need paper. In some ways, it's not so much that we discovered attention, which is a misconception, but it is the realization that literally, as the title says, you can throw away other parts and just build a network with attention layers. And it introduces a formula of self-attention, how one word pays attention to other words in a text, in a sentence. They brought in the terminology of key and query and value and so forth. So that's that. Now, I won't go too much into attention. We just assume that it is. But one basic idea about attention is paying differential weightage or emphasis to different parts of the input, different components of the input. So, for example, I gave the example that if you're hiking and you're enjoying the mountains and the sky and everything around you, and all of a sudden you hear a roar. Now your attention is at the bush. You're looking for that mountain lion, right? Or the coyote or something like that if you're hiking here at the Bay Area. Does that make sense, right? So that is differential emphasis you're paying to different parts of the input. What is your receptive field, the whole landscape? Yeah. That is attention. Now, this paper, as I said, attention is all you need, said that you can do natural language processing with just the attention as a construct. You can, in other words, altogether skip your RNNs, LSTMs, GRUs, etc. So that was a revolutionary statement. And the other practical consequences is suddenly you could do a lot more processing in parallel because those prior architectures are completely sequential in nature. You could also create deep networks, like stack them. People were not in the habit of creating very deep LSTM networks. So it brought depth, the ability to do deep stacking. It brought the ability to do parallel processing. It brought many goodies, but above all, from a theoretical perspective, it brought about the importance of using attention and its power, its core power. How much power attention has, actually, I would argue that we are still discovering, or why it works, we don't quite fully understand. And there are many, many thinkers who have come up with alternate formulations of this idea. They're still thinking about it. In particular, look at the works of one researcher, Chris Olah, who I think is at Anthropic at this moment, one ex-Googlers. He has a reinterpretation. This group, his whole group, has a reinterpretation of how attention works, which does not actually bring in that the key query value formalism at all. But so we are still figuring out what is attention, why it works. We know what it is, but why it works. People are figuring it out. Or rather, not why it works, but why it works so extraordinarily well. Now, what this paper is going to show you is just as for natural language processing, even when you apply transformers to computer vision tasks, then it is all you need, right? Like, or maybe a provocative title of this paper could have been, to see, attention is all you need, or something like that. Like for vision 2. Now you ask this question, didn't we just a little while ago go delve into the great power of CNNs? Then what is going on? And it turns out that, see, CNNs are very powerful. You can't take down the king of the hill so easily, right? So that's a pretty bold statement that it achieves state-of-the-art results with a transformer, but it does, and we'll talk a little bit about it. Right? So again, the main emphasis of this paper is two key results. First, you can actually do computer vision with transformers. Right? That's important, and here is a way to do it. And the second part is that if you were to do it, then under certain conditions, not always, under certain conditions, the transformers are better at the task, or at least achieve a similar state of the art. Right? Now, today we know that they're actually better at the task so long as the data sets are huge. Now, transformers, if you remember, they don't have much of an inductive bias. They are sort of attention networks, isn't it? But CNN, as we discussed, they have two very strong inductive biases. What were the two strong inductive biases? Locality, locality bias, and the other one is translation equivariance. Right? Locality means that you look first at the microstructure before it zooms out and looks at and reconstructs global meaning out of it, or feature maps out of it. That's the locality, just to recap. Translation equivariance is a cat is a cat is a cat, irrespective of where in the image you put it. Right? Because it will lead to the same feature map being discovered, but somewhere else. And you move the cat, its feature map simply moves to a different location. Right? And at the end of it, the final activation, the softmax, or whatever it is, will still classify it as a cat. So those are the properties. Whenever you induce a bias from your external world, understanding of the external world, what happens is it simplifies the model. And as we know, convolutional networks have far fewer parameters than even, for example, dense nets that you would do, MLPs that you would do, because it leads to a lot of sharing of parameters, which is a fancy way of saying we use the same filter all over the picture, isn't it? Now, and a very simple intuition is models with less parameters take less data to train, generally. Right? So convolutional networks actually can be trained to fairly high accuracy with reasonable data set sizes. But then we live in the world of big data. Right? And so I will continue here what it says from this point. We show that this reliance on CNNs is not necessary, and a pure transformer applied directly to sequences of images, image patches, can perform very well on image classification tasks. We pre-train on large amounts of data and transfer it to multiple mid-size or small image recognition benchmarks. This is important. This is how, do you remember how BERT was trained, guys? When we talked about BERT, it was trained on a very mass language model. Fill in the blank task, right? Trivial task. But once you trained BERT, BERT could understand the language. It had understanding of natural language now. And therefore, its ability, a pre-trained BERT could therefore solve a whole slew of downstream NLP tasks. So a similar statement is being made here. It is saying that, let me emphasize that. When pre-trained on large amounts of data and transferred to multiple mid-size or small image recognition benchmarks, blah, 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 a VIT, and they introduced the word vision transformer, VIT. This word was introduced in this paper, they construct, attains excellent results compared to state-of-the-art convolutional networks while requiring substantially fewer computational resources to train. Now, this is a very interesting statement. You see the strength and the weakness, both implicit in it, if you parse through it or unpack it. You need to train it, pre-train it with large amounts of data. Aren't you get that? We know that about transformers. They take a lot of data to train. But then it says, after you do that, then on downstream tasks, it tends to beat the benchmarks, the state-of-the-art with CNNs. Now, generally in research, you come up with an idea, it sort of works, people consider it promising, and then you refine it over the years and make it better and better. You have few moments in time when you come up with an entirely new architecture, and right off the bat, it topples prior architectures and benchmark that have been refined over 2 decades. So you see the implication of this in the abstract. Right? The other thing that it says is, and it brings about this whole world of transfer learning, that you take this thing, this pre-trained model, and then you want to train it for any specific thing. Okay? I'll give you an example. In a prior bootcamp, and in fact, it will be your bootcamp, in this bootcamp too, give you the task. and this will be your task, to train it to tell apart with higher accuracy than out of the box between two things, a pepper tree and a weeping willow. So let me actually give you that homework right now. So in California, pepper trees and weeping willows are all around us. If you have visited any parks recently, right? Do we all agree that we have encountered it in whichever park we go to? So you have to write a classifier that distinguishes between these two, and it should do better than out of the box classifier, right? But here is a caveat that I'll give you for this project. Those images should come from you. Right? In other words, don't download lots of pepper tree and lots of weeping willow images from the internet. Resist that temptation. Right? Become real real scientists. Go out with the camera or take pictures of pepper trees and weeping willows from different angles, different resolutions, and so forth. Go get pictures, and if you can, create a small data set. I advise you to create 100 pepper trees and 100 weeping willows. Please do that, and then fine-tune a model on those images. Why is that important? Like, why am I saying this? Say that? 100. 100 each. Yeah, the reason it's important, guys, is that, see, these data sets, right? We assume we download data set and we just use it. You'll realize that it takes a lot of hard work. Somebody's hard work to produce these data sets, high quality data sets. It's part of the whole journey. You will learn to pre-process those images because your camera will take very high resolution images. Right? That most likely you don't want to feed into your algorithm, into your models. You'll have to downscale it. And you will learn about the whole pipeline. Typically, if you look at these articles, quite often people download a ready-made data set. It's pre-cooked. You feed it into the model, output comes results, and you show, oh, how great the output is. That's not how this field works. Most real-life situations, you'll have to gather data. You'll have to tune the model yourself, process the data, manipulate the data. You'll have to tune the model, fine-tune the model yourself, and continue. So this will be your first exercise in fine-tuning a pre-trained model. Are we together? Right? And I'll post this, the detailed requirement on your in your portal. So, all right, we'll go into this paper and see what it does. The self-attention based architectures, in particular, transformers have become the model of choice in natural language processing. The dominant approach is to pre-train on a large text corpus and then fine-tune on a smaller task-specific data set. So this is transfer learning. What is transfer? This is what we do these days. Right? For example, Hugging Face is very popular because it's the hub for transfer learning. You take a pre-trained model, then you fine-tune it. Right? So these days, you can't pre-train these giant models yourself unless you have a bank of GPUs. Right? A typical H100 costs how much? Anyone knows? 40,000. Right? You will need like servers that have 8 of them and many of those servers to pre-train a model for a long time. If you try to, let's just say that it costs millions to pre-train a model, or tens of millions to pre-train a model these days. To fine-tune takes orders of magnitude less, at least 2 to 3 orders of magnitude less cost. In fact, if you don't do it on the cloud, you do it on your 4090 for image processing tasks, like for example this lab, you can do it on your 4090. You see the reduction, right? So transfer learning is pre-trained, which is unsupervised big data effort, big data, big hardware effort, plus fine-tuning. Fine-tuning, which is supervised learning, means you give it the answers, right? Because you're not doing it on mass language model or dummy task, you're doing it on some real task. Supervised learning. small data, small hardware. Relatively speaking, by small, you have to take it in context. If you try to, for example, fine tune the Llama 70 billion, you still will need at least 2 boxes with lots of A100s, but still smaller than the big one. But for all the labs in this bootcamp, I've designed it in such a way that you can do it on a 4090, which is sort of a sine qua non. You have to have a 4090 hardware. Either you reserve it in the cloud, or you, and in the afternoon we'll talk more about it, practical issues, or you just buy it, right, and stick it into the box. Or do it on Mac. Some people have a reasonably good mileage with Mac also. So transfer learning is the norm. So this paper goes on to, and I won't go into because I've sort of explained that they are related works. So if you look at the related works, and by the way, in the lunch, please do study this paper. Read this paper line. I'll give you the big ideas here. It says that people realize that attention is a good thing. What were they doing? They were adding attention to CNNs. Right? Does that look reminiscent of what people were doing in the NLP world? They were adding attention to LSTMs and RNNs. Right? What this paper says, and this is the crux of what it is saying you don't need CNNs at all. Right? The question is really, but they do put a caveat. They say that it takes a lot more to train this network. So you can't train a transformer network on small data sets, pre-train it on small data sets. You have, because it has no inductive bias. You realize that, right? There's no weight sharing, none of that. You just have a transformer architecture, vanilla. So think, like, one easy way of thinking is, just think BERT. Do we remember what BERT was? Right? You gave it the word vectors, all the words in a sentence, stuck in the position, and then you add a special token. Why did we add a special token in the beginning called CLS? No, that would be the one that would understand the entire context, and we will use it for prediction finally. Right? So the activation, the final hidden state of the of that CLS token as it went through the whole network, whatever came out, that vector would be the input to, let us say, a softmax or a few more deep layers and a softmax to make your prediction. Yeah. Because you can feed only one vector, right, as an input to that. So that was that. So look carefully at this image now. Let us see if we see all the telltale signs of it. First of all, it is an encoder-only model. Encoder, do you see that? Now, encoder is, BERT is that, right? Is the encoder-only side of things. What is happening? Now, here is a key insight. But where are the words? What they do is they break up the image, slice the image into patches, 16 by 16 patches, right? Square patches. And then they treat each patch as a word. Now, let's step back and think whether that's legitimate or not. See, in a sentence, a word and its proximal words together form a context, isn't it? In fact, the whole technology of word embeddings, word to vec, etc., is based on that premise, that a word also picks meaning from the adjacent word to it. In the same way, there's locality here, because if you're looking at a little patch, quite likely that its adjoining patches give you more information about that patch, isn't it? So there is a parallelism here. Now, what you do is you take that, and I can 16 by 16 pixels, I can linearize it, but in reality, there are 3 channels of it, RGB. So what I can do is 16 by 16 times 3, and I can flatten all of that into one vector. That is effectively your word vector. If I make it a word vector, and then you can throw in position embeddings, right? Do that. And once again, put a CLS token right here. The extra token you put in. Does it look to you exactly like BERT? After that key insight in which you linearize the patches into a sort of a word vector. And therefore the title, an image is worth 16 by 16 words. Right? You get that sense. And this is it, guys. If you look at this picture right away, you understand everything that this paper is going to say. in its methods. Go ahead.
I'm trying to understand one thing. So, let's say the 1 and 2 will be fed in together, and then 2 and 3 will be fed in together.
No. All of the patches become words there. The whole sentence is fed together, right? Transformer takes the whole sentence. Do you remember? So the whole image is a sentence. Little patches are the words in the sentence. And therefore, they have word vectors, word embeddings.
But the thing is, when we use BERT, right? We picked 2 words that were close together.
No.
And then one that was random.
No, that was, you're talking about the sentence encoder.
Yeah.
That is completely different. That used a BERT along with this thing, contrastive loss function. That is S-BERT, right? Sentence BERT. That is an entirely different thing from BERT itself. It uses BERT with the with a contrastive loss.
Yeah, I was thinking that this is trying to achieve the same thing. In other words, 2 16 by 16 patches that are together are related, but if you take a random one, it's not related.
It doesn't think like that. The loss function. See, I know where you're getting at. What you're getting at. Huh? So there is truth to what you're saying. That the first part is correct. That locality gives context, whereas a random patch will be out of context. That is true. Having said that, S-BERT, sentence BERT, is a different piece. That part is not, because that uses a completely different loss function, a different technology called contrastive loss, triplet loss. We don't do that here. This is just plain vanilla BERT kind of thing. Right? Sentence BERT is also based on BERT. It's nothing but BERT, but it uses triplets and causes a loss function based on triplets. Right? So here we're just staying with BERT-like architecture. Right?
Also for that, what is that extra learnable embedding?
In BERT architecture, remember you have one token. So here is BERT. The cow jumped over the moon. Cow jumped over the moon. Each of these words become word embeddings, but then you always put a CLS. You remember the CLS token. Why? Because CLS is meaningless. So there is no reason any one of the words will pay special attention to CLS. But CLS will pay attention to the sentence, right? Essentially. And so when this goes through the transformer network, whatever hidden state the CLS comes up with, you use that as a proxy for the meaning of this sentence, right? So this is your CLS. Think of it as your CLS token. Did you get it? That is it. And then you always concatenate the position embedding. You need to know what position this image was at. This little patch in the image was at. Right?
When we were discussing about that one, we did touch upon that CLS at the time. We talked only about the position vector plus the word.
Did I not talk about CLS?
I don't think
during
so.
BERT?
I don't think so. That's where like the blank is.
Oh, okay. So maybe I should do, then I'll take a little digression. So what you do is, in BERT, just to be brief, what you do is you add one more token in the beginning, a special token. And as all of these words go through, there are multiple ways of doing it, but this is the way BERT does it. At the end of it, suppose you are feeding it into a classifier. That's it. And in reality, you'll feed it through a few more dense nets, feed-forward networks, but forget about it. Suppose there is a softmax here. Now, what is the softmax expecting? It's expecting a vector, right? But you ended up with God knows how many vectors. Based on the length of the sentence, you have so many arbitrary many vectors. So what are your choices? There are basically very few choices left. One is you can just pool it, mean pool it. Take the average of all the vectors. There are people who found that works too, right? But the BERT guys, the way they worked it out is, they said, okay, here's the reason. We'll put a special token in the very beginning, and whatever its activation is, its logits are, right? The hidden state that it produces, the attention vector that it produces, eventually, we will treat that as an input to the softmax, right? And for them, it worked. So, I mean, you don't have too many choices. The other thing you could say is you can't take the max of it or something like that. Mean pulling is common, and picking a CLS token is activation of the CLS token is common. per bird.
So this is just a random.
It's just a fact. See, a lot of these things are done. You notice that with transformers and with a lot of this, there is a lot of hacking. There's a lot of experimentation. When something works, then people think, okay, why did it work? Okay. So that's how BERT is. BERT is just this. Yes.
Does BERT have, so do we need to, when it comes to data formulation, do you put the CLS manually?
No, the system adds it. And so when you give it to BERT, it will automatically add it quietly. Internally, it will add it. You don't have to do anything. It will just pretend it. So this is it. So here.
Is the CLS activated more by the words that have maximum attention?
In a way, see, CLS is paying attention to certain words. Imagine what words it's paying attention to is probably a measure of what is most important in the sentence, isn't it? Right? In understanding the sentence. And that's the way to interpret it. So guys, any questions? I hope you understand. It's a very simple architecture. If you get BERT, did I miss covering BERT? Did I skip BERT altogether?
I think the other day we talked about like you started with like we want to discuss transformer and BERT. We were able to cover only the transformer, not the BERT. I think that is a mistake.
That is what happened. Yeah. We never covered BERT.
Yeah.
Okay, guys. Then in that case, I apologize. I must cover BERT. So in the afternoon, I'll also cover the BERT paper. But then we are doing it backwards. Just take me on trust that basically it's a machine that in which you give it this extra token, and whatever it produces, you then feed into a normal neural network to make your prediction. You can tell it's a bird, a ball, a car, or what it is. Right? And how did I miss BERT?
No, because we didn't have the time.
Oh, we ran out of time.
We ran out of time.
Yes,
So
I apologize. We must cover BERT. You can't have a class on LLMs and miss the whole BERT family altogether. BERT is a big family. We'll do that. So this is it. Once you get this, there is nothing else to this paper except the results. The results are spectacular. When you look at the results and how well it does on the results, it is just spectacular. Look at the VIT. Everywhere it's a tall pillar, isn't it? If you look, yes, go ahead.
So in the sentence, like in the wording, there is a strong relationship. Let's say like a word has a strong relation with another word. Basically, like they will be mostly seen together.
Right.
That's how the attention.
Yeah.
But in the pictures, how do you do that? Like even when it is learning, how do you know this part of the picture has strong relation?
So think about it this way. Suppose you see a circle, right? And you suspect it's a cat's face. You would be looking out for the tail, right? Otherwise, you might think it's a wheel. I'm just making it very intuitive. So it has to look at long-range relationships. So
Asif, you said this works only if there's a large set of
data.
So are we talking millions or are we just talking hundreds?
No, millions. ImageNet, CFAR 10, CFAR, these are massive data sets.
So in our homework, when we do paper 3, we'll do
100 is enough. Because it's fine tuning. Remember, once again, to answer that question that was asked, what did I say? That fine tuning, the transfer learning is based on the concept that pre-training a model takes big hardware, big data. Fine tuning, this next fine tuning task is a supervised learning task labeled data, small hardware. So remember, you're fine tuning. You're not training a transformer from scratch. You can't. It's too expensive.
So in this diagram,
yeah,
we don't see a decoder. The reason we don't see a decoder because it's just a classifying.
Yeah.
But if you are going to create an image based on
generative
task, then we need to have a decoder.
Not necessarily. Life is more complicated. You can actually create generative engines out of just the encoder itself. But how we do that, what you need to throw into the mix to do that, let's keep it for later. But one very simple intuition could be that suppose I give you a sentence and You just have to predict the next word. Then you take the next word and again feed it back in with the sentence plus the next word to predict the next word.
Oh, you can use the same encoder.
Basically, you make the encoder into a
Oh,
decoder
okay.
effectively. And so,
One question here.
yeah, 1 second, hold on. Somebody there asked a question. Yeah, yes.
For fine tuning a large language model or a vision transformer, we need to also understand how the data set is being prepared.
Yes, you must. And generally, when you get a model, it's document. If it is a good model, it is typically foundational models are extremely well documented. Right? And they will give you the data set, some sample of the data set, and you just have to make sure that your data set is aligned to that. But more than that, with the coming in of Hugging Face, what has happened is a lot of this has been standardized. So long as you're conforming to the Hugging Face API and the model is conforming to the Hugging Face, just use the Hugging Face API, all will go smoothly. Shraddha.
Yeah. So as it this going back to CLS token for a second. So CLS token is added in Word because CLS stands for classification. So when we start the input, the CLS token contains the meaning of the sentence as a whole. And
in some sense, yeah.
If I find analogy with the vision model, now I have different patches. One patch contains the monument, as I saw. Other patch contains a pillar.
Yeah.
Third patch contains maybe a bird flying in the sky, something like that, right? So CLS token essentially it tells the image that this one is a monument, and it contains the overall classification, right? Overall sense of the entire image, right? Because this is a classification vector. We have to.
In a way, yeah, you can think of it like that. See, here is how I think of it. If somebody gave you an image and said, "What did you see?" The answer that you would give, in a way, you aspire that your network will learn. The CLS token would have learned that answer intuitively.
Literally contains the meaning of the entire sentence.
Sort of. Right? I mean, the hope is that it contains to various degrees. It does, but that's your best hope. Are we together, guys? Eh? So this is the Vision Transformer paper. But why is it relevant? Do you realize that it completely expands the areas to which you can apply transformers, isn't it? Now, if you think about it, a video is nothing but a whole collection of image frames and audio. So the question is, can we extend transformers to videos? Well, it seems possible. Can we extend it to audio? Well, how do we extend transformers to videos? We know how to extend it to images. To audio. How would we do that?
Convert the audio
to what? To text. Well, that's one way to do audio to text, but then who will convert the audio to it? It's like who's going to bell the cat? How do you convert a waveform, electrical waveform, into words?
So same thing with this
little segments, but then you will get a squiggly shape.
So
time series shape.
You're looking at somehow convert that to.
You need to convert it to an image. So the journey is you take an audio form and you convert it to a sequence of images. Right? And then after that, the VIT will kick in effectively. So here is how you do that. See, there is such a thing as a Fourier transform. What it does is, when you look at so let me give you the basic intuition of that.
When you convert image in the accent, the loss experience,
hold on to that part. Yeah, hold on. See, guys, everything that an image is, at the end of it, it is in time domain. And if you look at the amplitude, it is Y. So if you look at this microphone here, what does it contain? It just contains a transducer. There's a diaphragm as I speak, air waves, acoustic waves hit the diaphragm. They lead to electrical currents, electrical potential, which have, let me just call it the electrical signal, which will vary. Within this wave form is everything. It contains your amplitude. It contains the accent. It contains the timbre. It contains the whole richness is embedded there ultimately in just this two-dimensional image, two-dimensional graph. Isn't it? There's a lot in there in this image. Now, there's a technology which is called the Fourier. Fourier was a French mathematician. Transform. What it will do is, and what you do is you take a segment of the image, the sound, a 30-second segment, let's say. You focus only on that. Now what happens is that at any given point, this is how the waveform looks, right? I can do a Fourier transform. What Fourier does is it gives you a graph on a different axis, frequency axis. It will tell you that I see, so let's say frequency is 0 to frequency 20 kilohertz, kHz, right? How much of each frequency do I see, right? So, are we together? So, for example, when I'm speaking to you, if I'm speaking in a very shrill voice, high frequencies, right? Whereas when I'm speaking in lower frequencies, right? So there's a frequency distribution in any voice. So when a Fourier transform converts time series into frequency domain. So now at each point, I can extract the frequencies that are present in the voice. And therefore, what I can do is, then I can do something interesting. Again, go back to the time axis. Time axis. Time axis. And I can I put frequency here. At any given time, in the sound that I was speaking, little bit, whatever that function looked like is Fourier transform, produces all these different frequencies. I just give it just like color map, grayscale map. The more intense it is, the higher the value. Right? I can normalize that frequency into a scale, and I can give it a value. So what will happen? You will have a color map, isn't it? You'll have a intensity map of frequencies, different frequencies. This is your frequency axis. This is your time. As I keep speaking,
right? It's kind of heat map.
Sort of a heat map of frequencies over time. And each slice will tell you. And then from slice to slice, because obviously we don't immediately change frequencies. So this is called a spectrogram. Because spectrum is about frequencies. Right? Or spectral decomposition is another word of saying, in some sense, you're doing this. So now you do a little bit more for acoustics. It turns out that a human ear, it listens logarithmically. Right? It doesn't hear, like if you double the frequency, right? In lower frequency ranges, it won't be able to tell as much. At high frequency ranges, it will immediately tell, or something like that happens. I forgot in which order. So what people do is they take the log of frequency, log f, or sort of not log f exactly. Let's just say that MEL aligns it to human hearing. So for acoustic, what you do is you convert little patches of sound, little segments of the audio into MEL spectrogram. When I convert it into MEL spectrogram, what do I end up in? Images. Right? And you can do that. You can, for example, tell one of the projects, actually, Shrutik did, very nice project. He literally used this transformers and this whole technology to create a classifier between. Shrutik, would you like to talk about it?
Yeah, absolutely. So, I was talking more with Jenna earlier, actually, but pretty much what the project was is we used a vision transformer to create a classification between two audio types, so the dog barking and a bird chirping. So essentially I used a library to convert all of the sound files into spectrograms, as Asif mentioned. And this is essentially a visual representation of these audio files. So think of, if you're having trouble, if you don't know what a spectrogram is, think of it as it's literally just takes the decibels. It's almost like a heat map of what a sound looks like. So it's a visual representation of sound. And as we've been going over in class right now, these vision transformers essentially take these patches of these images and identify patterns between these patches in order to determine or to help itself eventually classify these sounds. So for example, we had the training data set after we fed the images of all the spectrograms of all the converted audio files to the model. It's able to create like patterns of, oh, this is what a dog barks sound frequency looks like based on the spectrum. This is what a bird's chirping sound frequency sounds like based on these patterns of these spectrograms. And so it was just a simple classification model.
All right, guys. So for those of you who are remote, and did you guys hear it or should I repeat it?
Can you please repeat, Asif?
Let me do that. So this was a project actually Shutek did as his internship here at Support Vectors last summer. And he did a great job. He started, it was his foot in the door to AI. And in his very first project, he did amazing work. The problem that I had given him for his learning was to distinguish between the chirping of a bird and the barking of a dog. And what he did is he took all of these sound waves, converted them into MEL spectrograms, which are sort of like the heat map of what we are saying, and then fed it into these transformer models to create a classifier. Right? And by the way, guys, you can see visually, if you ever look at the MEL spectrogram, you can see the distinction between, for example, when there is a car is going by and it backfires, and you look at the MEL spectrogram, you suddenly see a lot of energy right there in the MEL spectrogram. So they do have unique signatures for different sounds. So well, there we go. So you can do it for audio, you can do it for images, you can do it also therefore for video, which is a combination.
So this is using the transformer models.
It is the transformer. This is a transformer, encoder part of the transformer.
But we can do the similar thing with other models, like not transformer. So
yeah, you can do it with CNN. CNN is obviously the king, used to be the king of the hill, and still is
even
quite strong.
For the acoustic.
Yes, same thing you can do. You can do, in fact, today CNN models they haven't gone away. Many tasks they're doing quite well.
So what is the y-axis of the first?
Time. It's let's say the voltage. Like I was talking about this microphone. So if you look at this microphone, what does it have? It basically has a diaphragm, which is a transducer. Right? As I speak, my sound waves are hitting upon the diaphragm, putting pressure. A transducer converts that pressure into voltages, and it sends the voltage out as a signal. So phi is your signal.
Okay, and that gets converted to a frequency.
That if you do a Fourier transform, you'll get it. So that is how these things work.
Is there any particular library that we convert the sound, like any popular library that we convert from sound to the vectors that we can use?
Oh, yes, we will. All of it you'll do in due time in this course itself. In this work.
Is there most famous
they are, I mean, like, okay, just look into Hugging Face, you'll see it.
You can ask
Lots
him,
of
right? He should. Yeah. I mean, I was gonna say, if you guys are like really interested in the sound convergence, then my presentation is on the Support Vectors YouTube channel. So if you just search up my name on the Support Vectors YouTube channel, you'll see a full presentation, me walking through all the architecture and
in Python, there's so many libraries to do everything. It's a little dangerous to point out to just one, but they're quite mature libraries. And Shrutik's presentation is very good. Shrutik, could you please share it on the Slack?
Yeah, I'll put it
if you can just put it on the Slack. And I'll add it to the course portal also. It's good. for watching. So guys, I'll summarize it. This paper is a milestone paper. Great papers always open the door to more exciting work. And this paper did. Right? It opened the doorway. And what happened after that is quite remarkable. You can think of this as not just a beginning of, so this was the foundation, the starting point for what today we call visual language understanding, really, and understanding images as a visual language. It also opened the door, as you will see, the next paper we'll talk about, after doing BERT, I apologize, I didn't do BERT, is it opens the door to multimodal learning, or maybe multimodal I might keep for the next time. In that case, we'll just do BERT, 2 papers a week. I'll do BERT in the afternoon. And it is, if you knew BERT, it would be very simple. It's very unfortunate. I thought I had covered BERT, but I'll cover it right after this. Lunch. So guys, we will have a lunch break. After lunch break, we'll cover BERT, but after that, we'll cover your project. I'll walk through solutions or partial solutions to many of the questions that you guys have been having about your project. And hopefully that will accelerate you in completing your projects.
But this is amazing, right? Converting that voice into a image thing.
Oh, yes. See, people have been thinking about it for decades.
So then you can use this in like all different type of aspect, right? Like when it comes to maybe like, you have like a built-in clothing with some,
Absolutely.
yeah, you
Absolutely.
can use that to
Fashion, you can use it for image recognition, for like handwriting, for example, MNIST. MNIST has become too easy. But yes, you can use it for MNIST, you can use it for fashion MNIST, or you can use for any image classification. Therefore, I give you the homework. Classify between 2 of my favorite trees. I love to sit below those trees. That's why I'm giving you those trees. Weeping willow and pepper trees. How many of you like either of the 2 trees?
Yeah.
Yes.
Very nice.
Lovely trees, yes.
One thing I didn't get fully is, how is this better than CNN in the sense that how I saw the graphs, but I didn't get the intuition as to why is this much better than CNN.
Yeah. Okay, let me answer. I got a question from the audience. How is this better than CNN? That's a very good question. Why? See, you remember CNN came with many things on its in favor of. It started with 2 very meaningful inductive biases from the real world. Right? First of all, it started out with local perceptive fields that it would use as filters. Because of that, it also inherited from those as a consequence of some of its decisions in the architecture, locality, and the fact that you go from, because of pooling, you end up understanding an image at different levels of granularity or resolution. It came sort of baked into that as you have multi-layer CNN. The second thing is translation equivariance. So CNN came with very powerful things, because of which you could train it with less data. So I'll pose this question for you guys. So then why are the transformers worth using for image tasks? And let some mysteries remain for you to solve. Come back with the answer after lunch.